The Pacific Highway is the principal rural arterial road serving the coastal areas of New South Wales and Queensland between the capital cities of Sydney and Brisbane. About 16 kilometres north of Kempsey, the Pacific Highway crosses Clybucca Flat, a floodplain of the Macleay River. This section of the Pacific Highway was constructed in the late 1940s as a flexible pavement comprising up to 600 millimetres selected gravel. However, the effects of frequent floods on the silt, which forms the floodplain, bequeathed a legacy of deformed pavement, a reduced margin for safety, a rutted and potholed surface with ever-increasing maintenance costs. At the bend in the Macleay River at Seven Oaks, north of Smithtown, floodwaters from the river enter the floodplain. Floodwaters cross and recross the highway at several low parts before draining away in the north and south arms of Clybucca Creek. A flood-free bypass of the area would require the construction of a deviation 35 kilometres in length, thereby rendering such a proposition uneconomical. Normal rehabilitation of a weak pavement in a rural area is achieved by overlaying or building up, but after negotiation with flood mitigation authorities, it was conceded that pavement levels could not be raised, as floodwaters would be trapped on prime dairying country, rather than draining away into Clybucca Creek. Any increase in pavement thickness would have to be achieved by a lowering of the subgrade level further into the saturated silt. Extensive testing across the floodplain was undertaken so that the most suitable type of pavement could be designed and constructed. Investigations determined that the subgrade was composed of alluvial silt with the water table rising to within 100 millimetres of the surface. Alternative designs suitable to carry the 600 heavy interstate transports that use the highway each day were considered. Either a flexible pavement in excess of 1 metre deep of a granular material that retains strength when saturated, or a rigid cement concrete pavement were considered necessary to carry the vehicle loads. Field compaction trials using differing compaction techniques were undertaken on short sections on the silt, and the results are praised. It was noted that heaving occurred even with a light roller working on half a metre of crushed rock. It was decided that a continuously reinforced concrete pavement would be constructed on a mass concrete sub-base course. The likelihood of flooding during construction also influenced the ultimate design. A road constructed in this way would meet all the requirements of the evaluation of the various test results and site conditions. Thus, the following plan was adopted. The subgrade to be trimmed 360 millimetres below existing road levels. A mass concrete sub-base course 130 millimetres thick to serve as a working platform to be laid on the prepared subgrade. The continuously reinforced concrete pavement, 230 millimetres thick, then to be constructed on the mass concrete subbase. The 3-metre wide shoulders to consist of gravel laid on the mass concrete subbase and provided with a bituminous seal. A continuously reinforced concrete pavement, as its name implies, is a concrete road which has no transverse joints, so eliminating the most adverse feature of the conventional concrete pavement. The result is a structurally stronger pavement with improved riding qualities and reduced maintenance costs. The pavement is designed with heavy reinforcement so that fine cracks will occur at closely spaced intervals of 1 to 1.5 metres. The continuous longitudinal reinforcement will keep these cracks tightly closed, and load transfer across the crack will be maintained by aggregate interlock. Joints in conventional concrete pavements not only detract from good riding qualities of the road, but are a potential source of weakness because of the likelihood of the ingress of water, resulting in a pumping action developing beneath the slabs. The Pacific Highway at this point is heavily trafficked, catering for an average of 4,000 vehicles each day. During construction, one sealed traffic lane in each direction was maintained. There were also constraints on the work. Menacabrini Lagoon on the east and public utility services, water and telephone cables on the west. Excavation to the subgrade on which the mass concrete sub-base course was placed was carried out by conventional earth-moving equipment. A single-lane autograde trimmer spreader then trimmed the line and grade of the sub-base to fine tolerances. The trimmer spreader is kept on correct line and grade by electronic sensors, which are activated by a tight nylon string line accurately positioned along each side of the excavated length. Steel paving forms 130 millimeters deep were accurately located on the excavated subgrade. The forms functioned in the dual capacity of concrete formwork and rails on which the concrete spreader finisher moved. Similar steel form, 230 millimeters deep, were used for the pavement layer and were pinned through the mass concrete subbase. The transverse reinforcing bars, 10 millimeters in diameter, were laid at 500 millimeter centers. The longitudinal reinforcement is cold-worked deformed steel bars, 16 millimeters in diameter, laid at 140 millimeter centers. Splicing of these bars was staggered to eliminate any possible plane of weakness. A steel to concrete area ratio of 0.6% was adopted to control transverse cracking to intervals of about 1 meter. The formwork for the surface course was leveled to predetermined tolerances to overcome variations in surface levels in the mass concrete subbase. Aggregate for the concrete was crushed river gravel from the upper reaches of the Macleay River west of Kempsey. The concrete for the work was produced under close and systematic supervision at a batching plant specially set up at Fredericton, north of Kempsey, and transported to the site by transit mixer. For the mass concrete subbase, the minimum compressive strength was 8 megapascals. For the pavement course, the compressive strength was controlled within the range of 28 plus or minus 5 megapascals. Excessive strength would have increased the crack spacing and hence the crack widths. Shrinkage of the mix was controlled for the same reason. Concrete was coarsely spread by hand and then vibrated by poker vibrators. A concrete spreader finisher was used to trim the concrete. The machine consists of a frame travelling along the formwork and an auger and a finishing roller which traversed the frame. The auger strikes off the concrete uniformly across the pavement, and the cylinder consolidates and finishes the surface. As the operation of the concrete spreader finisher did not extend right to the edges of the work, some hand finishing was necessary. Minor surface irregularities were eliminated with bull floats worked from both sides of the freshly placed concrete. The finished pavement surface was then textured with a heavy bast broom as soon as the surface was free of bleed water. The concrete surface was then sprayed with chlorinated rubber curing compound, specified in preference to wax emulsion, which could have impaired the initial frictional characteristics of the finished running surface of the road. Special transverse forms and dowel rods for end-of-day construction joints were used, and this construction joint was scabbled before fresh concrete was placed. Quality control of the concrete was maintained at all stages. The slump specified between 40 to 70 millimeters was checked as each load was delivered, and compressive strength test cylinders were molded. Test beams for flexural strength testing were also prepared to check compliance with the design figure of 4 megapascals at 28 days, corresponding to about 28 megapascals compressive strength. At the free ends of the pavement, considerable movement would have occurred without some form of restraint being provided to improve friction with the subgrade. This restraint took the form of a toothed anchorage comprised of 3 reinforced concrete beams protruding below the pavement at each end. Any residual movement was accommodated by the provision of a flexible joint with the adjacent pavement. As the concept of continuously reinforced concrete pavements is relatively new in Australia, special instrumentation to monitor steel and concrete strains and temperatures in the pavement was installed at 4 locations. Instruments are monitored and readings recorded periodically, while a data logger is reconnected twice a year for a monthly interval during summer and winter. The construction of 5.5 kilometers of continuously reinforced concrete pavement was completed after 12 months' work in June 1976 at a cost of $400,000 per kilometer, including the cost of approximately $100,000 per kilometer for moving public utilities and providing a sidetrack for traffic. During construction, the site was covered by floodwaters on 3 occasions. But as a result of the choice of a mass concrete subbase and a concrete pavement, the entire project was completed ahead of schedule. Measurements made on the completed pavement surface with the profilograph and NASRA roughness meter indicated good riding qualities, thus vindicating the choice of a jointless concrete running surface.